In this video, we will look at two examples. The first is if you have a long charged rod, infinitely long charged rod, what is the electric field at a point P, which is at a distance r from it. And the second example would be if we have a large sheet of charge, so it's like a paper that's very, very large and it has charge on it, and we want to find the electric field at some distance from it. Our next example is of a long, thin, it doesn't have to be thin, but a long cylinder. So if you have a line source or a thin cylindrical source, but that's supposed to be large, so it's large on both sides, and the question is what is the electric field at a point here away from a long uniformly charged rod. So it's a long, okay, it has to be very long for this to apply, long and uniformly charged rod. The diameter of the rod will not matter, and we want to find the electric field at a point P. That's our point P. So in order to solve that, we make a Gaussian volume, which is a cylinder and same distance on the other side. So we have a cylindrical surface concentric with the rod. Now the electric we'll apply the equation. Phi equals Q in over epsilon naught equals the integral of E dot dA, and this is applied over the Gaussian surface.
फोन कर रही हैं आप उठाएंगे?
हाँ तो वो चल रहा है, फिल्म बन रही है. Okay, so now to solve this over the Gaussian surface, again we need to look at symmetry. So one is the symmetry of the angle and the other is the symmetry of the magnitude. So in this case, if we consider any element of this surface, from here the electric field cannot be going outwards in all directions, because then from another area it will also be going outwards in all directions, and the electric field lines will intersect with each other, and that can't happen. So the electric field lines have to go straight out. Well, they can be coming outwards and going in all four directions, or seen from the top they will go in every possible direction, but they will always be perpendicular to the direction of the rod, which means that over here if they will be going like this, and on the lower surface they will be going like this, and on this surface they will be going outwards, okay, from all sides. Now let's suppose that we have three areas. We have an A1 and a curved area A2 and the lower surface A3. Then we will do this integration over A1 plus A2 plus A3, and the E over, let's say, A1, E dot dA is going to be the integral of E dA and cosine of, well, E is this way and dA is the area is this way, perpendicular to the surface, and so the angle is 90 degrees, and that's true over the entire surface, and therefore this is 0. Similarly, the integral of A over A3 is also going to be 0, and we're left only with the curved surface. Now, in the curved surface, A2 over A2. Now, the electric field is always pointing outwards, and the area is also always pointing outwards. If we consider a view from the top, that's our area. Well, area is also going to be pointing outwards, and the electric field is also going to be pointing outwards. And so our electric field is parallel to A2 at every point. Secondly, because our Gaussian surface, this curved surface A2, is at the same distance from the rod over the entire surface, every point on it is at the same distance, therefore the magnitude of the electric field has to be constant over A2, or at all points on A2. And so because now we will say the flux is Q in over epsilon naught equals integral over A2 E dot dA. So now because they're parallel, it becomes E dA cosine of 0 everywhere, so which is equal to 1, and because E is constant, we can take it outside. And so the Q in, well, we still have to figure out Q in. So let's write it, and then let's write it here, and then we'll figure it. Q in over epsilon naught equals E dA, and dA is the area A2. Okay, the integral of dA over A2 is A2, and that is, if the radius is taken as R, then, and the length is L, then A2 is going to be 2 pi RL. And so we can replace dA with 2 pi RL. Now, how do we write Q in? So when we have a long uniformly charged rod, then the charge on it will become infinite, even if the charge per unit length is very small, because the length is infinite. So in this case, we will say that the linear charge density is lambda, and that is the charge per unit length. And that is the value that's given to us, that is per meter of length of this rod, it's going to have that much charge. Then the charge Q in will be the charge from here to here in this length of the rod, because that length of the rod, this part of the rod only, is inside the Gaussian volume, and this length is L. Therefore Q in is going to be lambda L, and we can replace Q in with lambda L. Therefore our flux is going to be Q in over epsilon naught, which is lambda L over epsilon naught, equals E2 pi RL, which gives us that E, bring this over the other side, lambda L over epsilon naught 2 pi RL. And we can see that the L's will cancel, and so we are left with a lambda over, now it's 2 pi R epsilon naught, so we'll write it as 4 pi epsilon naught R over 2. So instead of 2, we make it a 4 over 2, and then this part becomes K lambda and the 2 over R. And so our electric field E is 2K lambda over R. That's the magnitude of the electric field, is 2K lambda over R, which means that as R keeps getting bigger, the electric field keeps getting weaker, but not as 1 over R square, as it is for a point source, but as 1 over r. So it's not an inverse square law thing anymore, it's an inverse r. Now, as the last example, we'll consider the case of a large sheet of charge. So like this paper is charged, but it's very, very large. So it's an infinite plane charge. The charge is over a large plane, and let's assume that this is part of that plane and it's supposed to be very long in all directions, and there is a surface charge density on it given by sigma, which is the charge per meter square of this surface. So you take a square meter of this surface and it has a charge sigma, which would be coulombs per meter square. And then in order to solve it, we need a Gaussian volume or Gaussian surface, and that surface should be a closed surface that completely encloses some part of this infinite plane charge. We can't cover the entire plane. So let's take a cylindrical Gaussian volume. So it's a cylindrical volume that's sticking out. We take a circular area here, and we have a cylinder sticking out of it. Okay, so this is a cylindrical Gaussian volume, but because it has to be completely enclosing it, so it also extends on the back side and this is our Gaussian volume. That's like a cylinder or a cover, a cap kind of a thing, like that's on this side and also on the other side. And now we want to find the flux, which is Q in over epsilon naught is going to be the integral of E dot dA. So again, we have three surfaces. We have a back surface, which is, let's say, A1. We have this surface, which is A2, and we have a curved surface, which is A3. Now, by symmetry, if we look at this surface from the edge, then the electric field has to go straight out on both sides. The electric field cannot go at an angle, otherwise it will intersect. And our Gaussian surface is like this. Now, this electric field is parallel to this surface. So along A3, it's going to be parallel to A3, and therefore, if we change the integral of E dot dA over the entire Gaussian surface and write it as integral over A1 plus an integral over A2 plus an integral over A3, then the integral over A3 is going to be 0, because the area is perpendicular to the electric field, or the plane of the area is parallel to the electric field. The electric field is either going to go over it or it's going to go under it. So this part is 0, and the other two will not be 0. So for A2 is pointing this way, and A1, which is this area, is pointing this way. The area is always pointing outward from the volume, and the electric field is also pointing this way. So for both A1 and A2, the E and the A are in the same direction. Same here, the E is this way and A1 is this way. So in both cases, theta is 0. So the angle between E and A, E is parallel to A1 and E is parallel to A2 on both sides. So theta is 0. Secondly, because A1 and A2 are parallel to the surface and the distance everywhere is the same, and we can assume it's the same on the other side, therefore E is the magnitude of E is constant over the magnitude of E is constant over A1 and over A2. And because the magnitude of E is constant, we can take it outside the integral, and so our flux would be Q in over epsilon naught equals integral over A1 E dA and integral over A2 E dA. Now we can assume this cylinder to be of some radius or some area. What we have to figure out is how to write Q in, and we've taken sigma as the surface charge density, and therefore Q in is going to be equal to the surface charge density times this area, which is the same as A1, which is the same as A2. So you can write it as A1 or A2 or simply A. And now we can replace that here. So our flux is going to be Q in, which is sigma A over epsilon naught, is going to be E, and the integral of dA, we just write it as A because we'll just write it as sigma A. Both areas are the same. All three areas are the same. This one, this one, this one, and this one. So this becomes EDA, and this becomes EA and EA, or it becomes 2EA. So, and therefore, sigma A over epsilon naught is 2EA, and we can cancel out the A's, and we are left with E equals sigma over 2 epsilon naught, which means that the electric field is not a function of distance. So whatever is the electric field here is going to be the same if you keep going further and further away. The electric field does not decrease, and that's evident because the electric field is perpendicular to the surface, perpendicular to the plane of the surface, and it'll just keep going like that, and there is it's not spreading out, and therefore it should remain constant whatever the distance. And so we have E equals sigma over 2 epsilon naught for a infinite plane surface source. Now if the surface is not infinite, but you're close to this surface, so if the surface is this big but you're very close to it, then this equation would still apply. But as you get further and further away, well, the equation would no longer apply. Now Gauss's law is applied whenever we have, or we can find a Gaussian surface that gives us great symmetry. Otherwise it's hard to do the integration. With symmetry it becomes pretty straightforward.